Hi everyone, it's Miss B. I'm going to do a quick review of lessons 7.3 and 7.4 regarding right triangles, and specifically regarding the geometric mean, and there was a couple different theorems there, and then special right triangles. So within these two different categories, I'm going to break it down for you with what you should have learned. And when we're done, we'll do some practice problems and then a quick check. Okay, so here's the four different categories. The two categories that fall under the geometric mean are the altitude theorem and the leg theorem. The two categories that fall under the special right triangles are the 45-45-90 and the 30-60-90. The first thing we're going to recap is the altitude theorem regarding the geometric mean. Okay, so with the altitude theorem, you're going to have this image. This is simply a right triangle with an altitude, and the altitude theorem of the geometric mean allows us to find missing parts of any one of these right triangles that you see in the picture. In fact, there's 3 right triangles. Make sure you can identify all 3 of those right triangles. Now the proportion that we can set up using the altitude theorem involves clearly the altitude, which in this case I'm going to call A. We might have labeled it something differently in your notes, but I'm just going to call it A for altitude. Next, it involves the legs of each of these smaller right triangles. Let's label that one B. And let's label the length of this leg C. So the proportion that we can set up says that A, which is the altitude, is the geometric mean of B and C. That's the language. Here's the proportion. So B is to A as A is to C. Now let's talk about the leg theorem for the geometric mean using the same image. With this image, we have the right triangle, also with an altitude. But using the leg theorem, there's another geometric mean involving this picture. And it's not going to involve the altitude piece. That's not going to be a part of this problem. What this is going to involve is the legs of the larger yellow triangle. So let's call this leg X and this leg Y. So the leg theorem is going to involve the legs of the large right triangle and the hypotenuse of the large right triangle. The hypotenuse in this case is B plus C, all together. So the hypotenuse is B plus C. So let's set up this proportion. First of all, if I'm looking for the geometric mean that involves B, that means we're going to be using the leg Y. So the proportion here would be B plus C, the entire hypotenuse, is to the leg Y as Y is to B. Now if we wanted to find the geometric mean involving C, we would be using the leg X. So let's set up that proportion. We would say B plus C is to X as X is to C. Okay, so in case you missed anything, we just covered the altitude and leg theorems for geometric mean. So I'll give you one more look at those slides. Here was the proportion we set up using the altitude within this right triangle. And here are the proportions we set up involving the legs of the large right triangle with an altitude drawn. We don't use the altitude here, but it involves a right triangle with an altitude drawn. So now we're going to jump to special right triangles. And we're going to start with the 45, 45, 90, which just means that the triangle is an isosceles right triangle with two 45-degree angles and one 90-degree angle. And since it's isosceles, we know that the two legs are always going to be equal. In a 45, 45, 90 triangle, like I said, the legs will always be the same value. So let's call that x. They will always be the same. The hypotenuse of a 45, 45, 90 is always going to be the length of the leg, so x, multiplied by the square root of 2. In every scenario, this is going to be the case. Which means in some of our more complicated problems, if you're given an integer for the hypotenuse, let's call it h for hypotenuse, if you had to find the legs of this isosceles right triangle, you would then do the inverse of that and you would divide by radical 2. But remember, when you're dividing by the square root of a number, you have to rationalize. And in order to rationalize, you would multiply the numerator and the denominator by radical 2. This will always result in h times the square root of 2 divided by 2. Now let's discuss the patterns we discovered in a 30, 60, 90 degree triangle. So in a 30, 60, 90, you should notice the side opposite the 30-degree angle is always going to be the shorter side of the right triangle, making the side opposite the 60-degree angle always the longer side of the right triangle. Naturally, the side that is opposite the 90-degree angle is the longest side, which has the name of a hypotenuse. Remember, your shortest side is always your home base here, so we're going to call that x. Using your home base, you can then find the longer leg of the right triangle and the hypotenuse of a right triangle. The longer leg in this scenario of this 30, 60, 90 is always the shorter side x multiplied by the square root of 3. It will always work out that way as long as your two angles are 30 degrees and 60 degrees. Your hypotenuse will always be the shorter side multiply. So whatever you get for that shorter side, just double it and you'll have the length of the hypotenuse. Again, looking at a more complex situation, what if they don't give me that key, that home base, that shorter side? What if they give me the hypotenuse of a 30, 60, 90 triangle? And let's say it's some integer, let's call it h, maybe it's 10. Well, how would you find the shorter side? You'd have to do the inverse. You're going to take that hypotenuse and you'll divide that by 2. So there's your short side. Whatever number that is, if I'm using the example of h being 10, that would be 5. So then you would take that key and then you can unlock the longer leg of the right triangle, or you can use Pythagorean theorem. If you have two sides, you can always use Pythagorean theorem to find the third side. C squared, which is the hypotenuse, is equal to a squared plus b squared. So in a nutshell, these are the two patterns that you have to remember in regards to a 45, 45, 90 degree right triangle and a 30, 60, 90-degree triangle. Now let's see some practice problems before you take your quick check. On page 458 of your textbook, there is a little self-check quiz there that I did send out a remind text for you to try to do. It's not a homework assignment that was due, but it's good practice. So I'm going to go over these problems with you, and the quick check will very, very closely resemble these questions. Number 1 asks which segment's length is the geometric mean of AC, which is the hypotenuse of the larger right triangle in the picture, and CD, which is the leg of the smaller right triangle in the picture. Now think, which theorem would this be? Well, it's not utilizing the geometric mean involving the altitude. That's not part of the question. So it would be, therefore, the leg. So the answer to this would be CB. Because this piece, CB, is the geometric mean of AC and CD. This would be our proportion here. We would say AC is to CB as CB is to CD. So that repeated part there, that leg, we say that is the geometric mean. Number 2 is a 3-part question. It's asking for the length of BD, AD, and AB. So first, let's just start with BD. BD, you have to identify, is the altitude in this picture. But before we jump to any conclusions that we have to set up a proportion using the altitude theorem, you should first notice that it's also the leg of this smaller right triangle in the picture. And do I have 2 side lengths of that right triangle given to me already? I do. I have a side length of 6 and a hypotenuse length of 10. So we're just going to use good old Pythagorean theorem. Our c squared in this case is 10 squared. Our first leg is 6, and the leg we're looking for, BD, we can just call that B. Solving for B using the Pythagorean theorem, we get 64 equals B squared, which makes B equal to 8. So to answer question 2, the first part, the segment length of BD is 8. Now that we have that piece of information, we should label it in our picture as 8. So let's move on and find the length of segment D. AD is the leg of this smaller right triangle. Do I have 2 side lengths of this right triangle? No, I only have 1, the length of 8. So now I'm going to see if I can use one of my geometric means to set up a proportion and solve for AD. If you notice, we now have the length of the altitude. So we're going to go ahead and use the altitude theorem. Remember, this theorem states that segment BD, the altitude, is the geometric mean of AD and DC. So substituting in the values that we know and the values that we're looking for, I can call the length of segment AD x, and so we would have x is to 8 as 8 is to 6. And now how would you solve this? You would cross multiply. So we have 6x is equal to 64. So if we divide both sides by 6 to solve for x, we get x equals 64 over 6, which can be reduced to 32 over 3. So you can just leave your answer like that. Or if you wanted to give an approximated answer, it's approximately 10, and let's round to the nearest tenth. so 10 and 7/10. The last part of number 2 is asking us to find the length of segment AB. AB is the other leg of this larger right triangle in the picture. And you actually have two choices to go about this. You can use Pythagorean theorem because now we actually do have two sides of that triangle. If I draw it out for you, we know the leg CB is 10. We also now know the length of the entire hypotenuse is the 6 plus the 32/3 that we just found before. So if we add those together, we can find a common denominator, 18/3 plus 32/3. That gives us 50/3. So let's use that number for the length of the hypotenuse, 50/3. I'm not approximating this here as a decimal because that's not going to give me a very exact answer when I'm looking for the length of segment AB. So we want to keep it in that fraction format just because it's going to be more exact instead of rounding. So like I said, you have two choices, Pythagorean theorem, or you can actually use one of our geometric mean proportions. Let's start by using Pythagorean theorem. So C in this case is the hypotenuse, 50/3, so we're going to do C squared equals A squared plus B squared. So let's do 10 squared plus, we don't know what the segment length of AB is, so let's just call that our B. Alright, let's solve this for B. 50/3 squared is 2,500 over 9. Remember, you have to square both the numerator and the denominator. And then 10 squared is 100. Now to make our lives a little bit easier, because that 2,500 over 9 is a little bit ugly, let's just get rid of that denominator. So let's multiply everything by 9. Okay, so that's going to leave us with 2,500 equals 9 times 100, or 900, plus 9b squared. So let's subtract the 900. And so we have 1,600 equals 9b squared. Ooh, I like these numbers. They're pretty and fun and perfect squares, so this is going to be nice. So now let's divide both sides by this 9 because we want to get the b alone. So we will divide both sides by 9, and now we have 1,600, which is a perfect square, over 9, which is a perfect square, equals b squared. So now we have to take the square root of both sides to get our final answer. So the square root of 1,600 in the numerator is 40. The square root of 9 in the denominator is 3. So the length of segment AB is 40/3. Now, we could have used, like I said, the geometric mean. So if you want, I could show you how to set that up. I think I heard a resounding yes, Miss B. Please show us another way to solve this problem. So we're going to set up the leg theorem for the geometric mean to find that leg AB. Okay, so in doing this, we have the length of the entire hypotenuse of the large triangle, AC. We're going to compare that to what we're looking for, which is AB, and set that equal to AB over the length of that smaller leg, AD. Now, I warn you, this is going to get a little bit messy looking with this fraction, 32 over 3, but we can make it happen. So let's again just call the length of AB little b. It's unknown, so we'll just use that as a placeholder for now. And then everything else we have a value for. We have 8 and we have 32 over 3. And we also know the length of the entire hypotenuse is 50 over 3, as we saw earlier. So let's just fill everything in and solve this. So remember the length of that larger hypotenuse there? That was 50 over 3. And AB is our unknown, so let's call that B. AD is that smaller piece here, the 32 over 3. And now this is kind of ugly looking. We have a fraction within a fraction here for both sides. So we need to clean that up a little bit algebraically, and then things will be much nicer. So one really quick trick I showed you before, if you want to ever get rid of or eliminate a denominator, you simply multiply everything by that denominator, and then it's like magic, it goes away. So we're going to take this fraction and multiply the numerator by 3 and the denominator by 3. So in doing this, bye-bye denominator of 3, and we can now rewrite this problem as 50 over 3b. Much prettier. On the right side, let's do the exact same thing. Let's multiply the numerator and the denominator by 3. So in the denominator, I have this 3 divided by 3, which will leave me with a 32 in the denominator. In my numerator, I simply have b times 3, which is going to be 3b. Much better. Now we'll be able to cross multiply and we won't be driving ourselves insane. Now we have our 50 is to 3b as 3b is to 32. So we're going to cross multiply this and then solve for b. So we have 3b times 3b is 9b squared. And then 50 times 32 is 1600. Now this setup should look familiar because these are the same numbers we were getting when we used Pythagorean theorem. So now let's divide both sides by 9. And we have b squared is equal to 1600 over 9. Solving for b, we're going to take the square root of both sides. The square root of 1600 gives us 40, while the square root of 9 gives us 3. That leaves us with a side length of 40 thirds, or 40 over 3, which is exactly the same answer that we got when we used Pythagorean theorem. See, so multiple ways to do the same problem, whichever one floats your boat. So either way, AB has a length of 40 over 3. So that was all question 2. Nice and slow. Hopefully you caught on to everything. Let's finish with the special right triangle section by answering questions 3, 4, and 5. You always want to identify first, can I use Pythagorean theorem to solve a problem? Because that is a pretty helpful tool. In number 3, you can use Pythagorean theorem. You have two side lengths, 8 and 8, and you're just missing the third. But you also have a really nice, easy shortcut. You know that since these two side lengths are equal, in any isosceles right triangle, it's that 45 degree, 45 degree, 90 degree rule where we know exactly what the hypotenuse is. We don't even have to do any work. Using our rule, we know it's the length of the leg multiplied by radical 2. I didn't even have to use Pythagorean theorem there. I just know it from the pattern and the rule of 45, 45, 90. So that's number 3. Done. That's the answer. Moving on to number 4. this too is an isosceles right triangle. And I know it's isosceles because they label both of the legs y. And since they're using the same variable, they have to be the same length. So this time they give us the hypotenuse, which is always that more challenging scenario. So they give us the hypotenuse has a length of 10. So using our 45, 45, 90 rule, we're going to go backwards. And we're not multiplying by radical 2, we're going to take that value and divide by radical 2. That's going to give us the value for y. But we can't leave it just as 10 divided by radical 2. We have to rationalize. So if we rationalize this, we're going to multiply the numerator and the denominator by radical 2, leaving us with 10 radical 2 divided by 2. However, our final answer could be simplified even more because 10 divided by 2 equals 5 over 1. So our final answer for number 4 is 5 radical 2. Lastly, number 5, you should identify that it is a 30, 60, 90 special right triangle. We are only given one side of the triangle, so it's not possible to use Pythagorean theorem here. So we have to depend on the theorem we learned about 30, 60, 90 triangles and what pattern will always follow. I'm going to rewrite this one on a clean page and walk through it very carefully with you, step at a time. Identifying all the parts of this triangle, I know that this side length that is labeled 3 radical 2 is the long leg of my triangle. And I know this for a fact, not only because it looks like it's the longer side length, but because it's directly opposite the 60-degree angle, which means I know it is definitely the longer leg of the triangle. I also know for a fact that B, the length that is labeled B, is the hypotenuse of this triangle because it is directly opposite the 90-degree angle. And lastly, that makes A the short leg of this right triangle. So now that we know all of our pieces, we have to remember what the pattern tells us. We know that the short leg is always our key, or our x. We know the hypotenuse is always 2 times x. And we know the long leg is always that length x multiplied by radical 3. So let's take whichever piece we're given a numerical value for, in this case, the long leg. So we're going to start setting up an equation from this information. So we know 3 radical 2 equals x times radical 3. To solve this, we simply divide both sides by radical 3. But as you know, we can't leave our answer as 3 radical 2 over radical 3. We have to rationalize. So when I rationalize this, I get 3 radical 6 over 3. And those 3's will cancel, and the answer is simply radical 6. So now we have that key, that short leg. So I'm going to take that key, and I'm going to multiply by 2 for my hypotenuse. So my hypotenuse B is simply 2 times radical 6. So there you have it. A equals radical 6 and B equals 2 radical 6. That concludes our review. Good luck on your quick check.